Right now, as you watch this, you're moving through space at 2.2 million kilometers per hour. Not just because Earth orbits the Sun, not just because the Sun orbits the galactic center, but because something enormous, something with the gravitational pull of tens of thousands of galaxies, is dragging our Milky Way and everything around it toward a specific point in space. We call it the Great Attractor. It's located 250 million light-years away, in a direction hidden behind the plane of our own galaxy. For decades, we couldn't see it directly. The Zone of Avoidance, a band of gas, dust, and stars in the Milky Way's disk, blocks our view of that entire region of the universe. But we can measure its pull. We can track our motion toward it. We can map how it's affecting the motion of thousands of galaxies across hundreds of millions of light years. And here's what we've discovered. The Great Attractor itself is being pulled. There's something even larger beyond it, something so massive it influences motion across 1 billion light-years of space. The Shapley supercluster. And beyond that, possibly structures even larger, filaments and walls of galaxies stretching across significant fractions of the observable universe. Our galaxy isn't just moving through space randomly. We're falling, accelerating toward destinations we can barely see, driven by gravitational forces operating on scales that challenge our understanding of cosmic structure. Today, we map the largest structures in the universe and trace the invisible forces shaping galactic motion across billions of light years. We explore what it means that everything, including us, is being pulled toward regions of space we're only beginning to understand. In 1986, a team of 7 astronomers, Donald Lynden Bell, Sandra Faber, David Bernstein, Roger Davies, Alan Dressler, Roberto Turlevich, and Gary Wegner published something unusual. They'd been measuring galaxy velocities using a technique called the Tully-Fisher relation, which connects a galaxy's rotation speed to its intrinsic brightness. By comparing apparent brightness to intrinsic brightness, you determine distance. By measuring redshift, you determine velocity. Standard cosmology predicts galaxies should move away from each other due to cosmic expansion, with velocities proportional to distance, the Hubble flow. But the 7 samurai found something different. Hundreds of galaxies in our cosmic neighborhood showed peculiar velocities, motions that deviated from smooth Hubble expansion. And these deviations weren't random. They pointed in a consistent direction. The galaxies were being pulled. The team calculated that our local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller galaxies, was moving at about 600 kilometers per second toward a point in the constellation Centaurus. This motion was separate from cosmic expansion. Something gravitational was causing it. They called this mysterious gravitational source the Great Attractor. Galaxies don't just float passively through expanding space. They interact gravitationally. Dense regions, galaxy clusters and superclusters, have stronger gravity. They attract surrounding matter, creating flows toward overdense regions and away from underdense voids. On small scales, this is straightforward. The Virgo cluster, 50 million light-years away, pulls the local group toward it at about 200 kilometers per second. We can see Virgo directly, measure its mass, and calculate its gravitational influence. But the Great Attractor's pull is 3 times stronger, 600 kilometers per second, and its source lies in a direction we can't easily observe. The challenge: the Great Attractor sits at galactic coordinates roughly L equals 307 degrees, B equals 0 degrees. Latitude B equals 0 means it's right in the plane of the Milky Way's disk. Looking through the galactic plane means looking through tens of thousands of stars, gas, and dust. Optical light gets absorbed. Even infrared struggles to penetrate fully. This region is the Zone of Avoidance, about 20% of the sky where we're effectively blind to distant galaxies. So we had evidence of a massive gravitational source in the Zone of Avoidance, but couldn't see what was causing it. Throughout the 1990s, astronomers worked to map structure behind the Zone of Avoidance, using observations that could penetrate dust. Infrared surveys using 2MASS, 2-micron all-sky survey, and later Spitzer Space Telescope could see through some of the dust, revealing galaxies previously hidden. Radio observations of neutral hydrogen gas in galaxies provided another window. The 21-centimeter line of hydrogen isn't absorbed by dust, allowing detection of galaxies regardless of intervening material. X-ray observations from satellites like ROSAT mapped galaxy clusters by their hot intercluster gas, which emits X-rays. These surveys revealed structure. The Norma cluster, a massive galaxy cluster of over 10,000 galaxies, emerged from the data right where the Great Attractor's center should be. But the Norma cluster wasn't massive enough. Its estimated mass, equivalent to about 1,000 large galaxies. That sounds like a lot, but it's not nearly enough to explain the observed velocity of 600 kilometers per second across such a large region. You'd need the mass of tens of thousands of galaxies, a supercluster, not just a cluster. Further mapping revealed more structure: the Centaurus cluster, the Pavo-Indus supercluster, numerous smaller groups. Together, these structures form the Centaurus Hydra-Norma supercluster, one of the most massive structures within 300 million light-years. But even this wasn't the full story. In 1989, measurements of the cosmic microwave background, CMB, revealed something fundamental about our motion. The CMB, the afterglow of the Big Bang, is remarkably uniform across the sky, with temperature variations of only 1 part in 100,000. But there's a dipole pattern. The CMB is slightly hotter in one direction, toward Leo, and slightly cooler in the opposite direction, toward Aquarius. This dipole arises from Doppler shifting due to our motion. As we move toward Leo, CMB photons from that direction get blue shifted, higher frequency, hotter. Photons from the opposite direction get red shifted, lower frequency, cooler. From this pattern, cosmologists determined our solar system's velocity relative to the CMB rest frame, 370 kilometers per second toward galactic coordinates L equals 264 degrees, B equals 48 degrees. This is our total motion. Earth orbiting Sun, 30 kilometers per second, Sun orbiting galactic center, 230 kilometers per second, Milky Way moving through the local group, 100 kilometers per second, local group motion, 600 kilometers per second, all adding vectorially to produce 370 kilometers per second in the CMB frame. The direction pointed beyond the Great Attractor toward the Shapley supercluster, 650 million light-years away. Suddenly, the picture became more complex. The Great Attractor was real, but it was just one structure in a larger flow pattern extending across hundreds of millions of light-years. In 1930, Harlow Shapley identified an enormous concentration of galaxies in the constellation Centaurus. The Shapley supercluster contains over 8,000 galaxies spanning 400 million light-years. It's one of the most massive structures in the nearby universe. At 650 million light-years distance, Shapley is too far to dominate local dynamics, but its sheer mass, estimated at 10 to the 16 to 10 to the 17 solar masses, produces significant gravitational pull across cosmic scales. Modern surveys confirmed our motion toward Shapley. The dipole in the CMB and bulk flow measurements both point in its direction. But here's the complication. Shapley's influence alone can't account for all the observed motion. The mass and distance imply we should be moving at maybe 300 to 400 kilometers per second, not 600 kilometers per second. This suggests a combination of factors. Nearby structures like the Great Attractor accelerate us initially, while distant structures like Shapley provide additional pull in roughly the same direction. We're not being pulled by one thing. We're being pulled by a hierarchy of structures at different scales. In 2014, Brent Tully and colleagues published a revolutionary paper mapping our cosmic neighborhood using a technique called peculiar velocity surveys. Instead of just measuring redshifts, which include both cosmic expansion and peculiar motion, they mapped how galaxies actually move through space after accounting for expansion. The result? Laniakea, our home supercluster. Laniakea, immeasurable heaven in Hawaiian, contains roughly 100,000 galaxies spanning 520 million light-years. Total mass, approximately 10 to the 17 solar masses. The Milky Way sits on Laniakea's outer edge. The Great Attractor region lies near its center. The Virgo cluster, Centaurus, Norma, Hydra, all are parts of Laniakea. Tully's maps showed something profound. Galaxies within Laniakea flow toward its gravitational center, like water draining toward a basin. The Great Attractor is that basin's deepest point. But Laniakea itself is not isolated. It's bordered by the Perseus-Pisces supercluster, the Coma supercluster, and voids. and the entire structure is moving, flowing toward Shapley and beyond. In 2017, Yehuda Hoffman and colleagues discovered something unexpected: voids push. Cosmic voids, vast regions of space with few galaxies, have below-average density. In the expanding universe, this creates a gravitational repulsion effect. Overdense regions attract, underdense regions effectively repel. Hoffman's team identified a massive void on the opposite side of the sky from Shapley, a huge underdense region they named the dipole repeller. The dipole repeller isn't pulling us, it's pushing, or more accurately, we're falling away from it as space expands more rapidly in low-density regions. Our motion is influenced by both attraction toward the Great Attractor and Shapley and repulsion from the dipole repeller behind us. It's like a ball rolling downhill, except the hill is being shaped by both the valley ahead, attractors, and the plateau behind, repellers. This explains why our velocity is higher than attractors alone would predict. We're not just being pulled forward, we're being pushed from behind by expanding voids. Zoom out far enough, and the universe reveals its largest scale structure, the cosmic web. Superclusters form dense nodes. Filaments, strands of galaxies and dark matter, connect superclusters. Voids occupy the spaces between filaments. It looks remarkably like a three-dimensional spider web. This structure arose from quantum fluctuations in the early universe. Tiny density variations, 1 part in 100,000, grew under gravity over 13.8 billion years. Overdense regions attracted more matter, becoming more overdense. Underdense regions lost matter, becoming voids. The result? A universe divided into dense filaments and empty voids. The Great Attractor sits at a node where multiple filaments converge. Galaxy flows along filaments funnel matter toward nodes like Laniakea's center. When astronomers map galaxy positions using redshift as a proxy for distance, peculiar velocities create distortions. Galaxies falling toward a massive cluster have velocities directed inward. If you're on one side of the cluster, some galaxies are moving toward you, blue-shifted, appearing closer. Others away from you, red-shifted, appearing farther. This creates a fingers of God effect. Clusters appear elongated along our line of sight in redshift space. On larger scales, galaxies streaming along filaments toward nodes create pancaking effects. Structures appear squashed perpendicular to our line of sight. These distortions encode information about gravitational flows. By measuring how distorted structures appear in redshift space versus real space, cosmologists infer the strength of gravitational infall and thus the underlying mass distribution. Studies of redshift space distortions in the Great Attractor region confirm massive overdensities hidden in the Zone of Avoidance. The distortions match predictions for a supercluster of the estimated mass. Deeper X-ray and radio observations of the Norma cluster revealed it's not a single cluster, but a complex of multiple clusters merging in real time. The Norma cluster, ACO 3627, contains thousands of galaxies embedded in a vast reservoir of hot gas at tens of millions of degrees Kelvin. This gas emits X-rays detectable by Chandra and XMM Newton space telescopes. The cluster's velocity dispersion, the range of galaxy velocities within the cluster, indicates a mass around 10 to the 15 solar masses. That's significant, but still not enough alone. However, Norma is surrounded by other clusters, the Triangulum Australis cluster, the Circinus cluster, smaller groups. Together, they form the Norma supercluster, with total mass exceeding 10 to the 16 solar masses. This structure lies at the gravitational center of the Great Attractor region. Galaxy flows converge here. But Norma itself is moving. Its redshift indicates recession due to cosmic expansion, but its peculiar velocity shows it's also flowing toward Shapley. Even the Great Attractor is being attracted. In 2008, Alexander Kashlinsky and colleagues published a controversial claim: evidence for a dark flow, a coherent motion of galaxy clusters extending out to 1 billion light-years or more. The claim, galaxy clusters across vast distances share a common peculiar velocity of 600 to 1,000 kilometers per second toward a region near the constellation Centaurus. If true, this would indicate gravitational influence from beyond the observable universe, perhaps from mass concentrations in regions we cannot see, or from exotic physics related to cosmic inflation. The evidence came from measurements of the kinetic Sunyaev-Zeldovich effect. CMB photons scattering off hot gas in galaxy clusters get Doppler shifted by the cluster's motion, creating a small temperature distortion in the CMB. Other teams tried to replicate the result. Some found supporting evidence. Others found no significant dark flow beyond what known structures predict. As of now, the bulk flow debate remains unresolved. Most cosmologists think observed flows can be explained by known large-scale structures plus dark matter without invoking exotic physics. But the possibility remains that our local supercluster's motion might be influenced by structures beyond our current survey volumes. Here's a persistent mystery. When you add up all the visible matter in the Great Attractor region, galaxies, gas, dust, you get only about 10% of the mass needed to explain the observed gravitational effects. Dark matter fills most of this gap. Simulations predict dark matter concentrations in superclusters roughly 5 to 10 times the mass of visible matter. But even accounting for dark matter, some studies suggest a deficit. The velocities are slightly higher than expected, or the region of influence is slightly larger. Several explanations. One, underestimated mass. Deeper surveys might reveal more galaxies and gas than currently known, especially in the Zone of Avoidance. 2. Dark matter distribution. If dark matter is distributed differently than simulations predict, more concentrated or extended, it could affect gravitational potentials. 3. Relativistic corrections. At very large scales, general relativistic effects on structure growth become significant. Newtonian gravity might underestimate influence. 4. Bias in measurements. Peculiar velocity measurements have uncertainties. Different surveys sometimes give different values. Most likely, it's a combination of these factors. The mass is probably there in dark matter we haven't fully mapped, but the deficit reminds us how much we don't know about the universe's mass distribution at the largest scales. The universe's large-scale structure arose from gravitational instability. After the Big Bang, the universe was nearly uniform, but quantum fluctuations during inflation created tiny density variations, regions slightly denser or less dense than average. These variations were imprinted in the CMB at 380,000 years. The density contrast about 1 part in 100,000. Over billions of years, gravity amplified these differences. Denser regions attracted matter from surrounding underdense regions. Overdensities grew denser, voids grew emptier. By redshift z equals 6, 1 billion years after Big Bang, the first galaxies formed in overdense regions. By z equals 2, 3 billion years, large galaxy clusters existed. By z equals 0, today, the cosmic web fully matured. The Great Attractor and Laniakea formed through hierarchical structure formation. Small halos merged into larger ones, eventually creating superclusters. Dark matter drove this process. It doesn't interact electromagnetically, so it collapsed faster than normal matter. Dark matter halos formed first, galaxies formed within them later. This framework predicts structures like the Great Attractor as natural outcomes of gravitational instability plus dark matter. The cosmological principle states, on sufficiently large scales, the universe is homogeneous and isotropic, the same everywhere and in all directions. But how large is sufficiently large? Galaxies cluster. Clusters group into superclusters. Superclusters form the cosmic web. At what scale does this structure smooth out? Observations suggest the homogeneity scale is about 300 to 400 million light-years. Average over regions larger than this, and density becomes uniform. The Great Attractor and Laniakea span hundreds of millions of light-years, comparable to the homogeneity scale. They're among the largest structures near the transition between lumpy and smooth. This is important because cosmological models assume homogeneity. If structures significantly larger than the homogeneity scale existed, it would challenge our cosmological models. So far, observations are consistent. Yes, the universe is lumpy locally, but on scales of billions of light-years, it smooths out, as expected. The Great Attractor is big, but not so big it breaks cosmology. Dark energy, the mysterious force accelerating cosmic expansion, affects large-scale structure formation. In the early universe, before about 5 billion years ago, dark energy was negligible. Gravity dominated, allowing structures to grow. As the universe expanded and matter density decreased, dark energy became relatively more important. Today, dark energy makes up 68% of the universe's energy content. Dark energy counteracts gravity on large scales. It suppresses structure growth. Clusters still form, but more slowly than in a matter-dominated universe. This means structures like the Great Attractor and Laniakea are probably as large as superclusters will ever get. Dark energy prevents them from growing much more or merging into even larger structures. In a universe without dark energy, the Great Attractor would eventually collapse into a single massive cluster. But dark energy ensures this won't happen. The structure will remain a dispersed supercluster, with individual clusters separating as expansion accelerates. Our cosmic flows toward attractors will continue, but will never reach them. Accelerating expansion will eventually dominate, carrying distant structures beyond our cosmic horizon. Several missions and surveys are working to fully map the Zone of Avoidance. Wallaby, Wide Field ASCAP L-band Legacy All-Sky Blind Survey, using the Australian Square Kilometre Array Pathfinder, Wallaby is mapping neutral hydrogen in hundreds of thousands of galaxies, including those behind the galactic plane. SPHEREx, Spherical Photometric Survey, NASA's planned space telescope will survey the entire sky in infrared, penetrating dust to reveal hidden galaxies. LSST, Vera C. Rubin Observatory, starting in 2025, LSST will repeatedly survey the southern sky in optical and near-infrared, eventually mapping billions of galaxies, including many in previously obscured regions. SKA, Square Kilometre Array. When completed, SKA will be the world's largest radio telescope, capable of detecting neutral hydrogen in galaxies across the entire sky. These surveys will complete the map of our cosmic neighborhood, revealing all structures in the Great Attractor region with unprecedented detail. We'll measure masses precisely, map dark matter distributions, trace gravitational flows completely. Current peculiar velocity surveys have measured motions for thousands of galaxies within a few 100 million light-years. Next-generation surveys aim for millions of galaxies across billions of light-years. DESI, or Dark Energy Spectroscopic Instrument, is measuring redshift for 35 million galaxies. DESI will map peculiar velocities across the observable universe. Euclid Space Telescope, or ESA's mission, will measure shapes, positions, and redshifts for billions of galaxies, enabling peculiar velocity measurements at unprecedented scales. Roman Space Telescope, or Nancy Grace Roman Space Telescope, will contribute complementary data, particularly for distant galaxies. These surveys will answer key questions. Do bulk flows extend beyond known structures? Is the dark flow real? How well do simulations match observed flows? What is the detailed mass distribution of dark matter in superclusters? Within a decade, we'll have a complete map of mass and motion across the observable universe. Understanding the Great Attractor and large-scale flows tests our cosmological model. Lambda CDM, lambda cold dark matter, predicts specific patterns of structure formation. Observations of flows and structures either confirm or constrain this model. So far, observations match predictions. Structures like the Great Attractor form naturally in simulations. Bulk flows have expected magnitudes, but precision measurements might reveal subtle deviations. If flows are stronger than predicted, it could indicate dark matter properties differ from assumptions, warm dark matter instead of cold, dark energy behaves differently than a cosmological constant, general relativity needs modification at cosmic scales, initial conditions from inflation were different than assumed. Most likely, observations will continue confirming lambda CDM, but science advances through precision tests. Even small deviations guide theory. The Great Attractor, once a mystery, is becoming a tool, a natural experiment testing our understanding of cosmic evolution. Recent breakthroughs in computational cosmology allow simulations with unprecedented resolution. Comparing simulated universes to our observed universe reveals whether we truly understand structure formation. And increasingly, the answer is yes, we do. The universe makes sense. Gravity plus dark matter plus dark energy explains what we see. The Great Attractor is no longer strange. It's expected, a natural consequence of cosmic evolution. The Shapley supercluster lies 650 million light-years away. Beyond Shapley, surveys detect more structures, more superclusters, more filaments. How far does the gravitational hierarchy extend? The observable universe is 93 billion light-years across. We can only see structures within that radius, but the universe extends beyond, possibly infinitely. If structures exist beyond the observable horizon, they could exert gravitational influence we can't trace to a source. This is the idea behind the dark flow hypothesis. Maybe our supercluster's motion includes a component from mass distributions beyond what we can observe. Current consensus, probably not. Known structures within the observable universe account for observed motions. But there's uncertainty. Surveys haven't mapped everything. Dark matter distribution isn't fully known. Relativistic effects at cosmic scales add complexity. Within the observable universe, we're being pulled by known structures. But whether something beyond contributes, we can't definitively rule it out. Galaxy flows like those toward the Great Attractor raise philosophical questions about motion and reference frames. In an expanding universe, what does it mean to move? Every galaxy is receding from every other galaxy due to expansion. But peculiar velocities, gravitational motions, add to this. The result? Complex flows. Cosmologists use the CMB as a reference frame. The CMB defines at rest in the universe. Our velocity relative to the CMB, 370 kilometers per second, represents our total peculiar velocity. But the CMB frame is arbitrary, in a sense. It's convenient because the CMB is homogeneous and isotropic after subtracting the dipole. There's no absolute reference frame. Motion is relative. Cosmic flows are real, but only meaningful relative to chosen reference frames. This connects to Mach's principle. Inertia arises from mass distribution in the universe. Our motion toward the Great Attractor is both a consequence of and a contribution to the universe's total mass energy distribution. We're not separate from cosmic structure. We're part of it. Our motion shapes the gravitational field, which shapes other motions in an interconnected cosmic dance. Will we ever reach the Great Attractor? No. Dark energy is accelerating cosmic expansion. Eventually, expansion will dominate over gravitational attraction. Structures within Laniakea will remain gravitationally bound. The Milky Way, Andromeda, and the local group will eventually merge into a single galaxy. Laniakea itself will remain bound, with clusters continuing to orbit within it. But Laniakea will separate from neighboring superclusters. Shapley will recede beyond our horizon. Distant structures will accelerate away, crossing the threshold where recession velocity exceeds light speed. In roughly 100 billion years, galaxies beyond the local group will have receded beyond observation. Laniakea will be an island, a gravitationally bound structure in an expanding void. Our descendants, if they exist, will observe a universe containing only Laniakea. Everything else will have redshifted into invisibility. The Great Attractor's pull will continue, but the wider cosmic flows will cease as structures separate. We're living in a special time, a brief window when the universe is old enough to have formed structures, but young enough that accelerating expansion hasn't yet erased them from view. We can see the Great Attractor, we can map cosmic flows, we can trace our motion through the cosmic web. Future civilizations won't be so lucky. We began with a mystery. Something was pulling our galaxy and millions of others toward a point in space we couldn't see. Decades of observations revealed the answer. Not one attractor, but a hierarchy of structures. Laniakea, the Great Attractor region, the Shapley supercluster beyond, all shaping gravitational flows across hundreds of millions of light years. We learned our motion results from both attraction toward overdense regions and repulsion from underdense voids. We're flowing through the cosmic web, pulled along filaments toward nodes where structure concentrates. The Great Attractor is real. It's the gravitational center of our home supercluster, Laniakea. But it's not alone. It's one node in a vast network extending across the observable universe. This understanding validates our cosmological model. Gravity, dark matter, and dark energy explain cosmic structure. Simulations match observations. The universe makes sense. But mysteries remain. The exact mass distribution in the zone of avoidance is still being mapped. Whether bulk flows extend beyond known structures is uncertain. The nature of dark matter and dark energy remains unknown. Future surveys will answer these questions. Wallaby, DESI, Euclid, Roman, all will map our cosmic neighborhood with unprecedented precision. We'll complete the map of the Great Attractor. We'll trace every flow, measure every mass, understand every gravitational influence shaping motion across cosmic scales. And we'll do this just in time. Dark energy is accelerating expansion. The window for observing distant structures is closing. In cosmological terms, we're rushing to complete our maps before the universe expands beyond our view. Right now, at this moment, you're moving at 2.2 million kilometers per hour through the cosmic web, falling toward the Great Attractor, being pulled by Shapley, pushed by the dipole repeller behind you. You're part of cosmic flows spanning 1 billion light years. Your motion is determined by structure formation over 13.8 billion years. You're connected to the largest scales in the universe through gravity's invisible hand. The journey continues. The Great Attractor calls, and we're falling toward it, 1 second at a time, across distances so vast that light itself takes hundreds of millions of years to traverse them. We are cosmic travelers, whether we realize it or not.